Okay, ladies, we need to talk. We need to talk. So what are we going to talk about, you ask? Well, thank you for asking. We're going to talk a little bit about atomic physics. And we've been looking at the particle theory of light. And the next question is, where do these particles come from? We could have done this earlier, but it's at the very end of the chapter. So, by the way, again, Moonies. This is chapter, I'm on page, I'm on page 351, 351 of Moonies. That is the place to go. And try the questions at the end of the chapter, because I'll probably take some test questions from there, all right? So this is Moonies, page 351 onwards. Page 351, not from the textbook, but from Moonies. Okay, so where do those photons come from? Those little bundles, those little particles of light. This, if you remember from chemistry, electrons. We're talking about electrons, and electrons have different energy levels. Remember, they have the ground state, which is that's the lowest energy level the electron can have, all right? It's the lowest energy, just like you at the end of the day, after all the sugar's worn off, okay? Now, that's zero, n equal to zero. It's called the ground state. But electrons can have more energy. Woo! Okay, they can be up here at n equal to 1, higher energy level. Not n equal to 2, even higher energy level. N equal to 3, and then they can go up to 4, 5, 6, 7, 8. They can keep going up and up and up and up and up. Eventually, you get up to n equal to infinity, which, notice, by the way, it's a long ways away. Notice that the energy jumps get smaller and smaller and smaller as you go from 0 to 1 to 2 to 3. And keep in mind, we're not really talking about climbing up a ladder. All right? This is just electrons that don't have much energy, then they have more energy, then they have more energy. This is just a schematic to represent it. It does look a little bit like a ladder, and that is the analogy that we use. Notice there's nothing in between this line right here, which I got these numbers from the Moonies book, but they're made up numbers. They're not, if you look in the textbook, they've got more complicated numbers. These are made up, but they're nice and easy numbers to use. So we're saying that the lowest energy that this electron can have is negative 15 electron volts. Not negative 16, not negative 14, but negative 15. The next energy level up, n equal to 1, is negative 9. There's nothing in between. All right, again, it is a little bit like uneven rungs of a ladder. There's nothing in between. You cannot, for whatever atom this is, you cannot have an electron. It just doesn't exist anywhere in between. There is no negative 14, negative 10, or anything like that. There's nowhere in between. It's either here, or it's here, or it's here, or it's here, or it's gone. All right. When it gets past this, it's been ionized. It's gone. And so for this right here, going from negative 15, it's interesting that they make the energy at infinity. At infinity, they make the energy level 0. That's the energy at which the electrons left the atom. The electron is no longer in the building. All right? The electron has left the atom. This is at its lowest energy. How much energy is required to get that energy to ionize this atom? All right? Take that electron away. You need to add 15 electron volts to get it to here. Okay? At that point, the electron is no longer attached to the atom. That atom has been ionized. So they just express them with negative values. So to get an electron from the ground state and then ionize it, take it completely away, like in the photoelectric effect. If the electron is in the ground state, it would have to absorb a photon that is at negative 15 electron volts. If that electron absorbed a photon at negative 15 electron volts, then that electron would leave the atom and it would go, and you can provide a current if that's what's happening. What if the electron's up here? Well, it doesn't have so far to go. If this electron was already at n equal to 1, at a higher energy level, it already had that much more energy. What's that? 6 electron volts more than down here. Then you'd only have to add 9 electron volts to get it up here. So electrons are jumping up and down. They're not always just leaving the atom. They're jumping up and down all the time. So if you have electrons that are at a higher energy state and then they drop, where does the energy go? Let's look at an electron, for example, that goes from n equal to 1 down to n equal to 0. Because electrons don't remain in their excited state for all that long, right? They're excited, they're excited, they're excited, they're exhausted. They drop on down, then this is the lowest they can ever go. They're continually absorbing photons and then going to higher states and then dropping on down to lower states. Okay. Well, if you have an electron that's at n equal to 1 and it goes down to n equal to 0, then it loses energy. It goes from -9 to -15. And so delta E for the electron, that's the energy change. It's always final minus initial, okay? It's going to be, what's that going to be? -15 minus a -9, which is -6 electron volts. That's the energy change when it drops down there. Again, where does it go? Because, energy is never lost. It's never created or destroyed. It's transferred. Where does it go? It goes as a photon. All right, it disappears as a photon. Here's your equation right here it's a very simple equation. And as long as you get into your brain that change in energy of electron equals photon energy. Photon energy equals change in energy of an electron. Change in energy of electron equals photon energy. So this -6, going from -9 down to -15. What's the energy of the photon released? This is where we get light from. Let there be light. Where does the light come from? It comes from this. So that's the change in energy of the electron. So what is the energy of the photon? Notice the negative sign that's built into the equation here, all right? Right there. So that's -6 is 6 electron volts. So that photon has 6 electron volts of energy. Now, what's the actual wavelength of that? So, what color is that, for example? If you go over here, you already know this equation. This came from E equals HF. But we tend to talk about waves in terms of wavelength. So I'm going to put that, remember, just in case you forget, remember that V equals F lambda, or F equals V over lambda, or C over lambda in this case. That's where this all comes from, just in case you have forgotten. Your energies are all in electron volts. Your HC is 1240 electron volt nanometers. All right, electron volts, not joules. Electron volts, not joules. Electron volts, nanometers, not meters. Nanometers, not meters. Nanometers, not meters. Lambda is in nanometers. All right. So let's just go ahead and solve. That 6 equals 1240 all over lambda. So the wavelength of this, oh crumb, I don't have my calculator. An unprepared physics teacher, heaven forbid. So 1240 divided by 6 is 207 nanometers, which is shorter than visible. All right, visible light's around violet ends at around 400 nanometers. So that's in the ultraviolet range. Okay, I'm going to pause this because I'm almost out of time. I can't go over 10 minutes, and I'll start another one. So we'll finish this up. See you in a moment.